Okay, so we decided now this is growing kind of like a 1D problem, right? It's like a 1D conduction problem. So let's introduce a few concepts, and this is stuff if you had 364, you've probably seen this before, but it's a good refresher. So how do if you have to remember, how do thermal waves grow in a 1D problem? How do we characterize the growth of the thermal wave? Well, it's going to be something like this. So let's start with a thermal wave. We'll call that delta T. So how does delta T grow with a 1D conduction problem? Do we remember approximately? Yes, 2 square root of alpha T. Sorry, I can tell I'm coming back from spring break. My handwriting's terrible. Okay, so 2 square root of alpha T. So this is how the thermal wave is going to grow. But we have this T component here, and we don't have a transient problem. Like there is no time. This is a steady state problem for sure. So we have to introduce something that represents time. So how do we represent time? Well, time is just equal to the position x divided by the free stream velocity u infinity, right? So we have meters divided by meters per second. That gives us seconds, right? So our time here is this. And so we can say for this problem, for a convection problem, the thermal wave grows approximately like 2 square root of alpha times x. That's x over u infinity. Right. So this is our thermal wave growth. So now you say, as you move out in x, the thermal wave grows. Right. That becomes our variable for surrogate variable for time here. Okay, we can do the same thing for momentum. So we can say our momentum boundary layer is going to grow approximately like 2 square root of, let's say, something times u or x over u infinity. And what is that something? Well, what is it that is transferring momentum? Right, what is the property that transfers momentum? Yes. So we're going to put in here viscosity, and this actually is the kinematic viscosity. So that is the symbol nu, which happens to look a lot like a V, but I'll draw it with the 2 little hats on it, or whatever you want to call them. So we have nu, and nu is just mu over rho. Mu, the dynamic viscosity divided by the density. Okay, so let's write that out. Nu is our kinematic viscosity. That's equal to mu over rho, and that has units of meters squared per second. So you can see the units are actually the same as alpha, right? It's a diffusivity basically of momentum, meters squared per second. Kind of interesting. All right, so we do this for heat. We can do this for momentum. We won't do it in this class, but you can also do this for species diffusion, right? And you write the same thing. I don't know, you call it delta, I don't know, concentration or something like that. And that would be approximately 2 times some diffusive constant for a species times x over u infinity, right? It's the same underlying law. It's just a diffusion process. And it's the same thing for momentum, same thing for heat, same thing for a species, chemical species diffusion, right? So we have these kind of 2 concepts that we're going to move forward with, this delta T and this delta M, right? So let's just write out a couple ideas here. So we have alpha, and now we have this this nu. All right, so alpha for these problems represents, for us, it's the ability of a fluid to transport energy by conduction, right? So it's the ability of a fluid to transport energy by conduction. Okay, and nu, our kinematic viscosity, is the ability of a fluid to transport momentum. Okay, so those 2 things for a given fluid, we can actually compare them directly to each other. And that ends up being a really useful property. So the comparison of those things is called the Prandtl number. It's Prandtl, Prandtl number. Okay, and the Prandtl number is defined as the following. It is nu divided by alpha. Right, so it's our ratio of momentum transport divided by energy transport. All right. So this is, like I said, a really useful property. It's a fluid property, right? This is something that you'd go look up for a given temperature. You look up the viscosity, you look up the properties of conductivity, density, specific heat. That all goes into the Prandtl number. So we end up with this fluid property that tells us how good is this fluid at transporting momentum versus transporting heat. So think about like some examples here. What would be an example of a fluid that has a Prandtl number that's really low, right? So it's relatively good at transporting energy, not so good at transporting momentum. Sure, yeah, a liquid metal, right? Something that has a lot of, say, like free electrons, right? Something that can really move energy, but struggles to, or has no mechanisms for moving momentum, right? What would be kind of the other way around? Something that's really good at moving momentum, but not so good at energy. Water, sort of in the middle. Air, sort of in the middle again. Oil, for sure, right? Oil is a pretty good insulator, but it's a really viscous fluid, right? So you can kind of see how you have these different fluids that can line up that way. One example that I think is important is, so let's talk about air for a second. So air or any other gas, it's basically an ideal gas. What are the mechanisms for transporting momentum? Like physically, what's happening? It has the molecules have to bump together. They're relatively sparse. They have to physically come together. What are the mechanisms for transporting heat? It's about the same thing, right? They physically have to come together. So the mechanisms in an ideal gas situation are basically the same mechanisms. So anytime you're transferring momentum, you're transferring heat. So you'd expect the Prandtl number for a fluid like that to be what? 1, right? And it turns out air is pretty close to 1. It's something like 0.7. Okay, so you have to think about right, it's a property of the material, property of the fluid, and it really depends on the underlying energy and momentum carrier interactions that are happening. Okay. Okay, so that's the Prandtl number. One other important number we should get to is the Reynolds number. This is something I'm absolutely sure you've seen before. Reynolds number is RE is equal to density, rho, times some characteristic velocity, U characteristic, times a characteristic length, divided by mu, viscosity. So if you do this right, Prandtl number dimensionless, same units for nu and for alpha. Reynolds number is dimensionless. These are dimensionless numbers. Usually you'd see this in fluids like Reynolds is, rho times velocity times the diameter or something divided by mu. So our job and the main complication for the Reynolds number is we have to decide what are these characteristic velocities and lengths. And that depends, so I write this in red, these depend on the geometry. Right? These are things that are going to change based on your problem. So if you have a flow inside a pipe, right, it's the characteristic length would be the hydraulic diameter. If you have a flow over a flat plate, the characteristic length is not going to be a diameter, it's going to be distance over the plate, right? So these are all going to change depending on the situation, but the Reynolds number is, basically the same thing. Okay, let's see. So let's see, we came up with, this model here, right? So this thermal boundary layer thickness and this, not that one, this one here, the momentum boundary layer thickness, these are approximate models. If I were to go actually calculate the boundary layer thickness using this model, it's approximately going to be correct, but it's not exactly correct. So let's walk through a couple steps just to see how or what the kind of actual correct model is here. All right, so let's start with momentum. So delta M is 2 square root of nu times x over u infinity. So what we want to do is get this to kind of a form where we can compare it directly. So just follow the steps with me. So we're going to first divide by x on both sides. Okay, so we have, make sure to make that approximate. Delta m over x is about equal to 2 over x times the square root of nu times x over u infinity. Okay, and then we have delta m over x is approximately, we're going to bring the x on the right-hand side inside the square root. So we end up with 2 square root of nu over, it becomes x times u infinity. We're bringing x inside, so the x goes to the denominator. Okay, so this in here, let's see, this in here is actually one over the Reynolds number, right? So this becomes delta m is equal to, delta m over x is equal to approximately 2 divided by the square root of the Reynolds number. Okay, so this is an equivalent way of saying what we said over here. It's exactly the same. We just did some algebra to get there. Okay, the actual solution for this is delta m is equal to 4.91 divided by the square root of the Reynolds number. All right, so this is the actual, say, exact formulation for the boundary layer thickness for momentum. And so what's the difference? Well, we're just off by a little over a factor of 2. But our conceptual model is really close, right? Yeah.
Is the delta m above that divided by x?
Yes, it is. Thank you. Delta m divided by x. Yes, thanks. So this was our approximate. This is our exact. So an approximate model gets us most of the way there. Conceptually, we're seeing the same type of behavior where we're growing with the 1 over the square root of the Reynolds number, but there's a difference of maybe a factor or 2 or a little bit more in the boundary layer. All right. So if you're asked to calculate the boundary layer thickness, you'd want to use this guy here to be exact. If you're just proving a concept, you can use the approximate model. So we can do the same thing for the thermal boundary layer. So this becomes, let's just divide both sides over here by x, and then this becomes delta t over x. It's approximately equal to 2 square root of alpha over x times u infinity. Okay, so then this becomes, let's see, what do we do here? So delta t divided by x is approximately 2. Let's take everything in the square root and put it in the denominator, and then we're going to multiply by nu divided by nu. So what do I mean? So we'll say this is x times u infinity over alpha times nu divided by nu. All of that inside the denominator. We're just trying to get this to kind of something that looks similar to the actual solution. Right, so this is actually rho times mu divided by rho times mu. Okay, so then this becomes delta t over x is approximately equal to, let's see, what do we have here? So we have, so x times u infinity divided by x times u infinity times rho divided by mu. Right, that's the Reynolds number. Okay, so this becomes 2 divided by the square root of Reynolds. And then what's the other part? It's the Prandtl number. Okay. So that algebra gives us back the same thing as the momentum boundary layer. It's just now 2 divided by Reynolds times Prandtl. Okay. So if you think about that, right, that makes sense. There should be some relationship between the thermal boundary layer and how that grows relative to the momentum boundary layer and how that grows, and that relationship should be the Prandtl number, right? That's the definition of the Prandtl number, is how well it's transporting energy and momentum, right? Okay, so that's our approximate. So what is the actual? It is delta t divided by x is equal to 4.91 again, divided by square root of Reynolds times Prandtl to the 1/3. Okay, So again, we're pretty close. Let's label these. This is approximate, and this is the exact. So again, we're pretty close. We're off by a factor of a little over 2, the same factor. Reynolds is still square root of Reynolds, but then the Prandtl actually is a better fit if we take it to the 1/3 power. And why, so why are these two numbers different? Like what's fundamentally happening? A lot of it has to do with the definition of where the boundary layer ends. So one thing I didn't mention before, but so the boundary layer kind of definition is like 99% of U infinity, or 99% of say T, let's see, the temperature at whatever position minus T infinity divided by T S minus T infinity, right? So this relative temperature difference, 99% of that versus 99% of U infinity. So the difference is the exact one is actually using a slightly higher definition of that 99%. And there's also some other kind of physical mechanisms that cause it to grow more quickly. Okay. Okay, so we have this this model. Any questions on this? Okay. Yeah, this is again probably a lot of stuff you've seen before. Let's see, one other thing. Yeah, so fit it in down here. So one thing that we want to compare sometimes is the ratio of the momentum boundary layer to the thermal boundary layer, or vice versa. So this ratio, if we go through and do the algebra for this, we just end up with, let's see, 2x over square root of Reynolds for momentum boundary layer, and then the inverse of the thermal, which is 2x divided by square root of Reynolds times Prandtl. This is again our approximate. If we go through and cancel things out, right, 2x goes away, Reynolds, square root of Reynolds goes away, and we'll end up with the ratio delta M over delta T is equal to the square root of the Prandtl number. Okay, so this is kind of interesting. I mean, it just tells us if you want to compare the boundary layer thicknesses, you're going to take the square of that, or the square root of the Prandtl number, and that's going to give you that ratio. Okay, it's kind of interesting. Yeah. It's derived using something called a self-similar solution. So it is an analytical derivation, but I don't cover it in lecture because it's kind of long. But you can go, if you're interested, you can look in the book. It goes through this whole thing, self-similar solution. We might get to that eventually, but for now, it's just it's an analytical derivation.